Hello, welcome to Special Maths Academy. My name is Pius Ona, and today we'll continue with the solutions for fourth round Nigerian Maths Olympiad 2021 and problem 2. So, if you've not seen solution for problem 1, please check it out. All right, so let's get right into it. So this is a geometry problem. So we're going to get a sketch first. At the end, I'm going to display the proper diagram for this using the GeoGebra app. Okay, but for now let's just do it as we would. So we have a triangle ABC, then we draw the median from A. It meets the second circle again at D. Okay, so we have So we have A, B, C, and I'm just going to sketch the second circle. Okay, and the midpoint is here. Just call that M. So we're going to extend that, and we have T. Good. So let the circles passing through D, so one of which is tangent to AB at B, the other is tangent to AC at C. So I'm going to use different color now. So we have, let's just write. So tangent to AB, I'm just going to extend this a bit to make it clearer. It's passing through B and D, tangent at B. So that should look like this. Okay, and then we'll do something similar for C. So we extend it like this. Okay, so we have this. I'm just getting a rough sketch so that I have a good feel of how it might turn out if you're not constructing. Alright, so they meet again at E. So this here is E. There are some other elements that we have, but before I move on, I'm just going to prove something about E that will be crucial for this solution. Okay, so from this diagram, we have D line on the circle. So what we're going to prove here, E lies on BC. So that's the first claim. So let's call that claim 1. Okay, so to show that, we're going to look at the sum of angles on a straight line. That's just what we're going to use. So this angle here, let's start with this angle theta, and the aim is to show that the remaining angle here would be 180 minus theta. Then that will be a straight line. Okay, so we're looking at angle BED. Now, since AB is tangent to this circle BED, then we're going to have, by the alternate segment theorem, that this is going to be theta. And so that means angle ABD will be 180 minus theta by sum of angles on a straight line. Now ABD lies on the same circle as C. So that means by circle theorem, we get that this angle here, that's ABD, will be equal to the external opposite angle at C. So this here is 180 minus theta. And that external angle, now looking at the second red circle, that's a circle CED, you see that angle is actually the external angle of the angle we want to find. So these two angles here are equal. So this is also 180 minus theta. And once we sum that up, it means that angle BEC, which is equal to BED plus DEC, is equal to theta plus 180 minus theta, so that's 180 degrees. Alright, so that's a straight line, and then we have this. Okay, then I'm going to prove something else again. So to do that, we're going to introduce a new point, a prime. Let a prime be a point on the second circle of triangle ABC. So it's going to be a point such that a prime is parallel to BC, and A is not equal to A prime, as the case might be. So I'm just going to simply put it this way. So A prime is a point such that so a better description to this is a point such that A, B, C, A prime will be an isosceles cyclic trapezium. So as a matter of fact, we're going to prove this, that claim 2, that A prime, E and D are collinear. So meaning if you extend the line DE, it should pass through A prime. Of course, it might not look like that in the diagram. So I'm just going to resketch this. So we have, first of all, we have a circle. Okay, let's go with this. So this is just a sketch. A, B, C, as we had before. Extending this, you should have D somewhere here. I'm just going to put the key elements. Then if you draw these circles, so expect E prime to be on BC, and then we are looking at what's happening here. Claim that should be A prime. Okay, so once again, I'm going to redraw some of the red circles. So let's start with this one. Alright, so now once again we have that AB is tangent to that circle. So this angle here, which is the angle at B, so we just call that B, is going to be using alternate segment here. Once again, we equal to this angle here. So this is B. And now once this meets the point on the second circle, then by circle theorem, it means that the angle B will be equal to this angle here as well. So this is also B. That's based on the segment B and this point. So this point we claim should be A prime. Okay, so just looking at the base angles for this quadrilateral, you see that it's isosceles, at least based on the angles, and we can use that to show it's parallel. So for instance, since this angle here is B, it's going to be equal to the external angle here, so this will also be B, and so that means this is parallel. So meaning this must be the special point where if you draw a parallel line through A, it meets the circle again. So that's A prime, and with that we have that A prime, E and D are collinear. So we don't need to involve the other circle at this point. Okay, so we have two claims so far. Now we're going to actually move on with the problem. So go to the next setting, and then we'll do something similar and then combine the two. So say similarly, let the circles passing through D, one of which is tangent to BC at B, the other is tangent to BC again at C. So this time they meet at F. So we're going to give yet another sketch. Okay, so we have this. So A, B, C. So D will be somewhere here. Okay, now we want the circles to be tangent to BC. So it's going to be quite a big circle, extending this. The circle might look something like this, and the other one something like this, we get something of this nature. So this point here should be F. Okay. This is the median. This is M. All right, so we're going to claim once more. So this time this is claim 3, and the claim is that F is, or put it simply, M is midpoint of AF, or F is reflection of A over M. So to do that, we're going to actually prove something more, which is that ABFC is a parallelogram. So that's what we're going to show. And then once we've done that, then we know that the diagonals of parallelograms will bisect each other. So M will be both midpoints of BC and AF. Okay, so to do that, we're going to show first of all that. Okay, so we're going to do this once and for all. So we're going to establish a few things. Let me connect this and connect this bit here. Now we don't know if AMFD is a straight line yet, so we're not going to bother proving that itself. We'll prove something bigger, which is this parallelogram, and that will force them to be parallel, to be collinear. Okay, so the goal here is to show that this is BC is parallel to AC. All right, so for that, what we have now is that this angle, we call it say phi, be equal to, as an angle CAD is equal to angle CBD, since AB, CD lie on the same circle, so that's based on segment CD. Now, if we look at this circle, this right circle here, we have that angle phi is actually angle at the tangent. So it's going to, using the alternate segment here, is going to be equal to the angle DFB. Okay. So okay, I think we do need to show that AM, DF lie on the same line, and it's not too difficult. So what we have here is this angle, here is equal to, using the same alternate segment theorem, is equal to this angle here. Okay, and let's see. Okay, that might not solve the issue here. Okay, just a moment. Let me get things in order. Okay, so we have already had this angle here. This angle here is angle B. This is angle C. So this angle here is angle C. So I want to show that the shaded one is 180 minus C. Okay, I see. So what we're going to do now is so it's not so, I can't see a way to do this immediately, so I'm going to use a different approach. So I'm going to use the idea of phantom points. Okay, so the idea is that we're going to start with f prime such that AB f prime C is a parallelogram, and from there we're going to prove that f is the same as f prime, and then we still have what we wanted. Okay, so let's do that from that perspective, so that will be much easier to work out. Okay, so we have A here, and we're looking at f prime. So we're doing this in a way that this is already a parallelogram. So meaning, like we mentioned before, where the two diagonals meet, that will be M itself, and D of course lies on that line AM. So D is on this same line, AM D f prime. Okay, and then we have that if this is phi, then this angle here is also phi by alternate angles, since AC is parallel to BF prime. Okay, now I'm going to redraw this red circle. So from the red circle, we have by alternate segment theorem that angle MBD will be the same as DF prime B. Okay, so we have this to be also phi, which is equal to this one here. So ultimately, that means that sorry about this. Mix it up. Okay, so I'm just gonna readdress all this. So now we're trying to use phantom points. So let's do this carefully. So first we have this parallelogram f prime. Okay, and we draw diagonals. We know they intersect at midpoint of BC, so that's really M. And we know D is somewhere here. Okay, but we also know that D lies on a circle ABC. So if you start with this as phi, then by the mere fact that this is parallel, this will also be phi. And now the original phi as well will be equal to angle DBC. So this is phi. Angle DBC, so that's because of circle ABCD. Okay, so at the end of the day, now if you compare the last two phis we got, these two, then we see that they are alternate segments, and by alternate segments here it means that BD f prime, if you draw that circle, then BM will be tangent to that circle. So sketch a circle passing through this, then it means that BC is tangent to it. So this means that f prime lies on the circle passing through B and D that's tangent to BC. So it lies on circle BDF, where F is the original one. Okay, so it lies here, and then in a similar fashion, when we consider the other circle, you see that it's going to also be tangent. So F prime actually lies on circle CDF. So it means that F prime must be a common point to those circles, but these two circles will intersect at D and at F, so F prime must either be D or F prime is F, and F prime is clearly not D because of it has to be parallel, since this angle here, angle at A, is actually equal to the angle here, while on the other hand the angle at D is 180 minus that, so they are different. So this means that F prime is going to be equal to F. Alright, so that brings us to that bit there. Okay, so now move on to claim 4. Alright, so for claim 4, we have to bring in G. So let's go back to the problem. So finally, let G be the point diametrically opposite of A on the circumcircle of ABC. Okay, so if we bring in G, we have ABC and F from the parallelogram, T somewhere here, so this A, B, C. Okay, and then G is when we take center here, let's say this O, and we extend this to form the diameter, so this is G. Okay, so now this is M. Alright, so now the claim here is that GF is parallel to OM and is hence perpendicular to BC. Okay. Alright, so from what we have, AM is equal to MF, so that's M is midpoint there, and also from the radius of circle ABC, we have that AO is equal to OG. So that means if you look at triangle AGF, then O is midpoint of one of the sides and M is midpoint of another side. So it means that if we connect that, it should be parallel with GF. It should be half of the length GF. Okay, so that proves the parallel path. And obviously, since O is the center and M is midpoint of a segment, then this is a right angle. So that completes claim 4. Alright, so now finally we try to put everything together. So now let's go to the last, the main problem. So we want to show that DE and FG intersect on the circumcircle of ABC. And now we know that DE meets the circumcircle of ABC at A prime. So what it really remains to show is that GF also meets the circumcircle at A prime. So all three of them meet at that A prime. So A prime should be that point of intersection. So the final stuff we need to show is that A prime, G, and F are collinear. Okay. Remember what A prime is? It's supposed to be a point that makes A prime parallel to BC. Okay. So the way we're going to do this is that we already know that GF is parallel to OM and is perpendicular to BC. So we want to show that GF is actually also perpendicular to AA prime. So we know this, which is on the other hand perpendicular to BC, but BC is parallel to AA prime. So if we connect this automatically, it means that GF is perpendicular to A prime. Okay, so they may not meet at A prime, but wherever they meet, it must be at right angle. Now, on the other hand, if we look at A prime G, you see that it's going to also be perpendicular to A prime, and the reason for that is because AG is diameter, so the angle it sustains here will be right angle. So that means connecting this once again, we have that GF and A prime G must be parallel. So since they both pass through G, they in fact must be the same line. So G, F and A prime collinear. Alright, so it means that GF passes through A prime, the circle also passes through A prime, and DE also passes through A prime, so they all meet at A prime. Alright, so that brings us to the end of this problem. So I'll see you in the next one. Okay, so here's the diagram for the problem we just solved. Alright, so just in case you need a very clear diagram to work with, I decided to make use of sketches so that you get a proper feel of how it generally should go. Right, so you might not have very nice diagrams per se, but you're able to come up with same ideas. Alright, so see you then.